Okay, welcome everyone to the today's final air quality session. And as a reminder, there's also a following air quality session on Friday morning. So hopefully we can see everyone there as well. So yeah, welcome. This will be Air Quality Science Serving Society. So along the theme of the CMOS Congress this year, with a specific sub-theme on how that relates to air quality. So we've got a full set of 6 presenters, so we should get started. So our first talk will be given by Braden Nilsson, an AQ map, a real-time interactive map of PM2.5 in Canada from low-cost and regulatory monitors. So whenever you're ready, Braden. Thanks.
Perfect. Okay. Hi, everyone. Thank you for letting me share my presentation today. My name is Braden Nilsson. I'm working in the Western Air Quality Science Unit of Environment Canada, and I'm also a Master Science student at the University of Northern British Columbia, working with Dr. Peter Jackson. I'll be presenting on an interactive mapping tool we've been developing over the past several years, which we have named AQMap, that allows for anyone to visualize fine particulate matter air pollution observations in real time from both regulatory and low-cost monitors. Before I get into that, though, I would like to acknowledge UNBC and Environment Canada for all their support and funding during this process, as well as my wonderful co-authors. So fine particulate matter, or PM2.5 pollution, has become a hot topic in Canada in recent years, as wildfire smoke season has become an almost unavoidable annual event. The data shown on screen here from a study by Matz et al. 2021, where they mapped the May to September average wildfire attributable PM2.5 across Canada using data from the firework and GEMMAC models for the years 2013 through 15, as well as 17 and 18. From this, we see that the Western provinces are hit the hardest, with peak concentrations tending to occur either in southern BC or along the band of boreal forest crossing over the prairies. And just for reference, I wanted to include something similar for last year's smoke season. So here's some data from a NASA satellite looking at black carbon column mass density for July 21st, 2021. And note the dense smoke plumes moving across Alberta, Saskatchewan, and most of southern Manitoba, as well as a relatively abnormal amount hitting the maritime provinces. Historically, monitoring of PM2.5 in near real time has been through federal equivalent method, or FEM monitors, or FEM monitors. I'll say a mix of both throughout this. Given the monetary and time cost required to set up and maintain these monitors, however, they tend to be sparsely distributed in Canada, resulting in many underserviced populations. Here we see the current FEM stations on our map in Western Canada. Note the large areas, especially in the north and across the prairies, which do not have real-time observational PM2.5 data. Now I'll add in the low-cost PM2.5 sensors or monitors, or small sensors from Purple Air, as shown on the map as circles, and then also from our AQAG, shown as squares on our map. These small sensors contain 2 Plan Tower PMS 5003 nephelometers, which each independently monitor PM2.5. And they've grown in popularity in recent years due to their good agreement with FEM observations and their relatively low cost to purchase and maintain. Our group is actively working with agencies in Canada to supplement the current FEM network with these monitors in order to obtain PM2.5 information in areas which historically have not had observation data. Yukon, BC, Alberta, and Saskatchewan show the most dramatic changes in the West, and we should see quite a few more pop up in Manitoba as well this year before the smoke season kicks off, especially with the amount of smoke they were inundated with in the previous fire season. Eastern Canada has seen a similar growth of small sensors and also appears on our mapping tool as well. But I've chosen to focus on the West for this talk, given my own familiarity with the region, as well as the prevalence of wildfire smoke impacts. So we developed our mapping tool in order to make it easier for air quality health managers and members of the local communities to be able to visualize observations of PM2.5 in real time from small sensors and regulatory monitors alongside contextual layers such as modeling and forecast data. We also advocate for the use of these small sensors to provide as accurate as possible concentration information for regions and locations historically underserviced by the regulatory network, as well as for determining where the smoke is actually touching the ground, not remaining in aloft in the atmosphere like we get from most remote sensing platforms. First, I'll give an overview of AQMap and how it works and how you can use it. And then I'll talk briefly about our correction model we use to provide the best possible data from these small sensors. And I'll finish off with some implications for the upcoming smoke season based on what we've seen in past years. So AQMap can be accessed by going to cyclone.umbc.ca/AQMap in your web browser. The link is at the bottom of the slide there. We display hourly average PM2.5 concentrations in mass units for small sensors and FEM data across Canada. The data are updated every 10 minutes for the small sensors and every hour for the FEM monitors. Currently, only an English version is available. However, we're in the process of finalizing a French translated version as well, which should hopefully be released before this August. When using our tool, it's important to note that the small sensor data have a correction model applied to them in order to bring their readings more into agreement with the FEM monitors. I will discuss this correction model briefly on a following slide, but I'd also refer you to our upcoming publication for more information. The color scale we use matches that for the AQHI Plus system, using 10 micrograms per cubic meter 10 microgram per cubic meter bins up until a concentration of 100 micrograms per cubic meter. This top right menu can be used for controlling the mapping layers. The first 3 let you choose the base map. The following 5 control which observation data is displayed. Here you can switch out the corrected small sensor data for the raw if you so choose. And the remaining 4 options are contextual layers relevant to PM2.5 and wildfire, such as the most recent firework model output, the model which Jack Ten was talking about in the previous session. The top left side has the zoom and view controls. And just below that is a search bar for locating observation data based on the site name. If you click the circled question mark located in the bottom left, a large about the map info box will appear. And there's a lot of information in here that I'm not going to go through in this talk, but if you scroll down, you can find information on our correction model, which I'll just pull out here quickly for reference. And lastly, if you want to see the actual data from a specific location, you can click on any of the sites to see a pop-up of recent observations, as well as generate graphs if desired. So just a quick example of what that looks like. This is for a monitor located in Prince George, BC, named UMBC PA2. This is a purple air monitor. At the top is the monitor name, followed by a link to zoom into that monitor if it's not already zoomed in, like we see here. Below that is a statement of the current AQHI Plus category, so whether this hour's concentration falls under low, moderate, high, or very high, followed by the assigned health message for that category, again, all taken from the AQHI Plus system. Note that we'll be adding Quebec data soon, which will not include this messaging, given that Quebec uses an alternate system. Following this messaging, there is a summary table which contains the data type, so whether it's raw or corrected data if you have a small sensor, and then if it's a small sensor or if it's a FEM, the date of the last recorded observation, and then several time averages for quick reference. Clicking the plot time series button will create an interactive graph showing the last 2 weeks of hourly data. And you can select any period within the past year to visualize data using a calendar interface at the bottom, or you can manually hold shift and drag the chart left to right to scroll back and forth in time, or just click and drag to zoom into an area. Since the small sensors we use have 2 plant hour sensors monitoring PM2.5 within them, you can see how well those 2 sensors compare. We, by default, look at the past 2 months. If you click on the Compare Sensors AB button, here we automatically flag invalid observations based on the agreement between 2 sensors. There's more details found in the pop-up when you hover over top of it, but essentially we just look at the relative and absolute error for that hour to determine if they're performing similarly or not. And lastly, for the small sensors, you can compare with the data from a nearby FEM if there's one within 30 kilometers, both before and after applying the correction model we developed. Again, looking at the last 2 months of data. Here, the correct observations are in green, uncorrected are in yellow. And if you hover over a point, it'll focus on that data set and open a pop-up showing the date of the observation, as well as the FEM, and then the raw and corrected small sensor observations. We're in the midst of publishing our work on the small sensor correction model. However, the preprint is already available at the DOI provided at the top of the screen. From this work, we selected the displayed correction model form taken from Kiley et al. 2018. We fit a hygroscopic growth value of 0.24 using our 32 co-location sites across Canada and the US. And we also replaced any hourly relative humidity values less than 30% with 30%, and the same for those greater than 70% being replaced with 70. We evaluated this model alongside 7 other models using the AQHI Plus system and 15 co-location sites in Canada and the US. And I included a quick sample of that here at the bottom of the slide. Note that I've taken out the comparisons for models 3 through 8, and model 2 is the one that we truly care about for this talk in comparison with that no model row at the top. This model improved the average purple air FEM AQHI Plus bias for all but the very highest concentrations, And we were most concerned with the performance in the moderate to high range, given that this is where the concentration accuracy is of higher importance for health managers. This past wildfire smoke season, we saw a dramatic spike in users of the website, consistently nearly tripling with a peak of almost 10 times larger than normal. Daily unique users tended to be around 50 to 30 before July, climbing to between 50 and 100 and spiking to over 200 on July 27th of 2021, before lowering to the 50 to 150 range and settling again below 50 daily users. So the AQ map is definitely being used during the wildfire season, and we hope that with the rapid growth of small sensor installations, upcoming improvements, including Quebec data and a French translated version, and presentations such as this, that we see similar, if not larger pattern this coming smoke season. Here's an example from the 2020 wildfire smoke season, taken in mid-September from an older version of our map. The colored contours are from the most recent at the time fireworks smoke model outputs, showing the modeled concentrations of PM2.5 as a result of wildfire. Circles are the purple are small sensors and diamonds are the regulatory FEM monitors. And it's worth noting that many more monitors, including the AQ-AG monitors in their entirety, have been added to the map since this screenshot was taken in 2020, especially in the Western provinces shown here. So even though the screenshot is old, I feel it's a great example of the information small sensors can provide us during the upcoming wildfire smoke seasons. And I've highlighted a few regions here where the purple areas were providing additional spatial information not captured entirely by the FEMs. And as the coverage in prairie provinces increases, we'll continue to gain further information for air quality health managers to be able to understand which communities are being impacted and act accordingly. So just to wrap up, I have a quick animation from back at the end of January showing the site, the website in action when concentrations were a bit higher. This is looking at a site down in Washington. AQ-AGs were not included in this version of the model. They were added shortly after this animation was made. And then I would like to end just a few key points that I hope you all walk away from this talk with. First, the primary thing is I hope that I was able to give you all a good overview of how and why you would use our mapping tool. And I've included the link there again for anyone who missed it that still wants it. Second, I wanted to underline the importance of small sensors for getting observation data in underserviced communities. And lastly, I wanted to emphasize that small sensors are great for knowing which wildfire smoke is touching the ground and not just a lot still in the loft in the atmosphere, so we can see which communities are being impacted right now. So with that, I would like to thank you all for listening, as well as my wonderful co-authors, UNBC and Environment Canada, for their funding and support throughout this project. Cheers.
Thanks, Fred. That's really interesting. I was going to say, feel free to share that link in the chat. Any questions?
Hi, thanks for the presentation. Actually, we've actually started using, just so you know, using the purple air sensor outputs for some of the evaluation work with fireworks. And this has been really tremendous because of the distribution of surface measurement that's now available to us. One thing that you mentioned about being able to distinguish smoke being aloft and versus the smoke staying on the surface. I'm just wondering, how do you actually do that? Maybe you talked about it and I missed it, but maybe you can elaborate it out a bit. Thanks.
For sure, great question, Jack. Yeah, so where I was trying to get out with this is that one of the concerns with small sensors and purplers that have come up over the years is that it's not a regulatory level measurement, right? It's not kept to the same standard as an FEM. You're not going to get as exact of a concentration as you would get from an FM monitor, and you can't be as for sure about that measurement as we are about a FM monitor. But what it's great for is if you have smoke touching the ground, say in a community, the purple area is going to read high. It's going to read higher than it normally would read in that area, or than a nearby purple area that's not being impacted by the smoke would be reading. So while you can't necessarily nail down that this is the exact concentration in this area with a purple area, you can say, yes, given that there's smoke aloft and these concentrations are high from the purple area below, we can assume that the smoke is mixing down and actually impacting those on the surface. Great question, thanks.
I'm glad you asked, Jack. I was going to point out the similarities between Jack's talk at the end of last session and your work. This is, if this could be tied into weather forecasting and like
Mhm,
you said, there's a lot of potential overlap there, which is great.
for sure.
So yeah, thanks. So yeah, we should move on. Our next speaker is Eric Ward from my own group at York University. And Eric will talk about modeling the atmospheric transport of microplastics. Share. Looks great. And presentation mode.
Yes, let me just video
So, yeah.
quickly and all right, and still the proper screen.
Yep, that looks great. Whenever you're ready.
Perfect. Awesome. Thank you, Mark. All right, so like Mark said, I will be presenting my research on the atmospheric transport of microplastics. I am currently a master's student at York University, and my co-supervisors or also co-authors on this work are Mark Gordon and Ronald Hansen. So a quick introduction on microplastics themselves. So they've generally been defined as being plastic particles that are smaller than 5 millimeters in size. For atmospheric purposes anyway, in terms of the transport there, we're going to be dealing with micro scale, so generally even smaller in the micrometer range. Primary research on microplastics has generally been more towards the aquatic systems rather than atmosphere, as you can see from, if I grab a pen, from this figure here, there's been roughly just less than 500 atmospheric publications. And these numbers here were just published in a paper a couple weeks ago, actually. So as you can see, slightly less than 500, whereas for marine applications, there's well over 5,000 publications. So it is still a relatively new area. So given that, along with this figure up at the top right, it is the exact burden of microplastics in terms of the atmospheric contributions is generally unknown at this point. So we are looking to enhance that knowledge there. So this presentation and my work focuses on the main question of what role shape and size play in the overall transport distance of microplastics. So the three things that we're doing to answer that, so how do we quantify the emission rates and locations of microplastics? How do we model them? And then once we model them, how do we analyze the results? So going into the first step of the emissions of microplastics, we're generally looking at modeling tire wear product, or essentially abrasion from vehicles and such as what's called VKT, or from VKT data, which is vehicle kilometers travel data, which was fortunately provided to us from Environment Canada. So that data, which has experimental values, which have been determined in previous papers from 2018. So this data is separated into three categories. So your CVKT, or cars, which are generally your 4-tire passenger vehicles, your MVKT, or mid-size vehicles, such as your small moving trucks and such, and then your larger TVKT, or your large transport trucks. So in milligrams per kilometer, you've got about 20 for the smaller vehicles, and then about 200 milligrams of tire wear for these larger vehicles. So to analyze the data that was provided, here's a bit of a diagram as to show what data was provided. I used ArcGIS to analyze it. So looking at the first circle here is all of the analyzed or spatially analyzed data for the Greater Toronto area. So all of this would be collected into one emission source for all cities within Toronto. So that'd be Toronto, Mississauga, Hamilton, etc. And then all the VKT within each data set, within each data point. And each data point here is in a 10 by 10 kilometer grid, which makes calculating the overall area in that much easier. The second area here would be London, Ontario, which is much smaller, but given the top 100 most populated cities were chosen as a rough point, or as a rough emission estimate. So from that, about 18 cities were in Canada, and then the remaining 82 from the top 100 were within the continental United States. So as an example for the GTA here, so from this data here, we would get the average latitude, longitude from these set points. The height, which would be input into the model itself, was 10 meters for every, so that was consistent for everything. So for the GTA, the yearly average rate taken from the data provided by Environment Canada was about 300 kilograms per hour of microplastic, or at least of tire wear emissions based on the experimental values given here. And then the total area, like I said, was essentially a summation of the VKT points, which when input into the model anyway is in meters squared. So going into the actual model itself, so high split was chosen. This is essentially what it stands for. However, nowadays it's more complex than that. So that's not really an acronym that they use very much anymore. However, it is a complete system for computing like complex transport, dispersion, and deposition. And the dispersion and deposition aspects of it are what we're looking at in this research. So the main equations that we use, or at least high split uses, are these equations down here. The highly outlined ones are the more heavily outlined ones. So the first equation on the left here is a sphericity factor, which is the main way that we are determining the shape. So that ranges from 0 to 1, with a sphericity of 1 being a perfect sphere, and then the remainder from 0 to less than 1 being some sort of either fragment or simulated fragment or fiber. And they're all treated as being cylindrical in shape for simplicity. The other equations here, so the K values are a shape factor or a correction factor for non-spherical particles. RE is your Reynolds number, and then CD is the coefficient of drag, all of which are then input into the final settling velocity equation, all of which, so all of the equations here, aside from the sphericity, high split calculates itself, so there is no manual input for that. So going into the different shapes and sizes of these microplastic particles that we are going to emit. So the first decision was on the particle diameter. So we went with bin sizing from another study that was done at Environment Canada. So going along with what they found, we chose 4 bin sizes ranging from 2.56 up to 20.48 micrometers in diameter, which provides a good range of, again, particulate matter in PM 2.5 and PM 10, which is roughly where large interest is in microplastics, or at least for atmospheric transport. And then within high split for 20 total sizes, or 4 bin sizing times 5 bins per size, the total diameter range was 1.68 to 23.5 micrometers in diameter. So that gives a final weighting distribution, which is very similar to laboratory studies of tire wear, where about the largest proportion was below PM10 in diameter. So about 65% there was below PM10, and then the remainder was between about PM10 or 10 micrometers and the 23 micrometers that we found for the maximum. So for the specific shapes of these plastics that we want to simulate, so in an example for our median of 10.24 micrometer diameter. So for the shapes, we decided on 4 shapes. The first 2 are fragments, and then the last 2 are more fibrous shapes. So for the first fragment shape, the D over L is diameter over length aspect ratio. So the 0.64 aspect ratio was actually the modal aspect ratio of roadside tire wear products found in a study from, I believe, 2020. So from the aspect ratio there, it would then be converted over to the sphericity factor, which would then be input into high split to calculate for all of the different, so for all the 20 diameters, each sphericity was input for that to get a total of 20 sizes per like diameter. Yeah, sorry. And then for the 10.24 micrometer diameter length, the length is represented here to give sort of an idea on the different sizes. So for the fragments, they'd be generally more compact. And then for the fibers, so the short fiber would be a bit longer, And then the long fiber would be about 1,000 micrometers or up to a millimeter in size. So it'd be very thin and long. So some early results that we've seen. So for this, I decided to essentially condense it down and just show 3 cities of emissions. So for this, I chose Vancouver, Edmonton, and Calgary as the emission sources for this. And the particle diameter was kept constant at the largest 23 micrometer size for this diagram here. The interesting things that we found was the maximum concentration of the deposited microplastics onto the ground was much higher for the perfect spherical particles. So the highest concentration in, see the latest pointer, in the, or right next to the source locations was higher for spherical versus a more fragmented or fibrous particle. And this is the median or one of the middle sphericities of 0.58, which is a larger fragment, smaller fiber. And then in terms of the transport distance or coverage area, the difference in the coverage area is highest for the larger particles. So from this diagram here, the main takeaway is the summation area. So for the more fragmented particle of sphericity 0.5, the total area was a little over 5.2 million square kilometers. And for the perfect sphere, it was slightly over 4.3 million. Which would result in a difference of about 20% for the area. So the more fragmented or less spherical particle, I should say, had about 20% higher coverage area. So a brief discussion and conclusion. So the high split model, when we're looking at our results, show or suggest a greater coverage of microplastic transport for the non-spherical particles with the extreme fibers and such transporting over much further distance and a larger area compared to the more spherical particles or even the smaller fragmented particles. The larger diameter particles are transported a shorter distance as expected. So if you look at PM 2.5 particle compared to up to a 25 micrometer diameter particle, the PM 2.5 or 2.5 micrometer would be transported much further. However, the shape factor, so the non-spherical component of it, so longer fiber, would have a greater impact in distance of coverage for these larger diameter particles. And then the accurate shape parameters look to be a very key component in modeling of the atmospheric microplastics. And then down here, just to finish off, these are 3 important, or at least what I found interesting and important papers highlighting, I guess, the ecological impact, such as in human blood, and then more of an environmental impact of these microplastics, such as in their hidden contribution to snow melting, which would hint at something like changing albedo potentially, and sort of like enhancing a feedback loop for global climate change potentially. Although more research does have to be done in all aspects there. This is all my references that I used, and thank you everyone for listening. Is there any questions?
Yeah, feel free to unmute and go ahead if you have any questions.
Hi, Eric. I was just wondering, do these particles change at all on the timescales that they're being transported over? Like I would expect that they're going to degrade, the longer fibers break into smaller fibers and things like that. But I have no idea what the timescale for that would be. Do you think that might have any impact on your results?
So generally the timescale that we're looking at, so they were all modeled over the course of a month for July 2021. So in terms of like breaking down, I think that's a good point for like the longer fibers, especially as if some sort of enhanced forcing or weather conditions would break them down into smaller particles. That could definitely have an impact. I haven't looked at changing like the properties of them within the model as they're being transported yet, but that does bring up a good point on the potential changes that they could encounter after their release from the source.
Okay, thank you. I was also not even just mechanical, I was also thinking a lot about photo degradation. I think especially for the smaller ones, that might be an important process. That was interesting. Thank you.
time for maybe one quick question if someone has. Oh, otherwise it's exactly 25, so that's pretty good timing. So
Perfect.
let's switch. So our next presenter is Rhythm Reed, again from my own group at York. And Rhythm will be presenting on non-exhaust particle emission factor of vehicle traffic in an urban canopy. So whenever you're ready, Rhythm.
Can everyone hear me?
Sounds good.
Perfect. Thank you so much, Professor Gordon. Hi, everyone. My name is Rhythm Reed, and I will be doing an analysis on non-exhaust emissions within non-exhaust vehicular emissions within urban canopy. So road traffic emissions are very important within urban atmosphere just because of the high amounts of pollution that we get. And emissions from vehicles are released from two distinct sources. Exhaust-based emissions, which come out of your tailpipe, and they include smaller particulate matter, NOx, CO2, and non-exhaust emissions. And these are the ones that we're interested in. These are bigger particles that originate from brake wear, tire wear, and resuspension of road dust. Preliminary studies have focused mainly on correlating the particulate matter to vehicular traffic. They've also worked a little bit on how particulate matter, how changing traffic patterns such as higher congestion can lead to higher non-exhaust emissions. What we're questioning is if we do make small changes such as reducing the vehicle speeds in urban areas and congested areas, allowing for more free-flowing traffic, how that can improve air quality. So non-exhaust emissions are larger particle sizes. They're greater than 500 nanometers. Brake wear is the first one, which arises from lining material and brake discs that are broken down from grinding of brake pads. The second is tire wear, which arise from the shear force between the tire threads and the ground. And the third is resuspension of road dust. Road dust have a few different types of sources. These are generally coarse materials, and they can originate from the abrasion of the road and they can arise from construction zones as well as industrial constituents. There's also been studies done in which light-duty vehicles and heavy-duty vehicles affect how resuspension of road dust varies. Where heavy-duty vehicles, there's a higher amount of resuspension of road dust due to vehicle-induced turbulence, which is called VIT. The location for our study was in central Toronto. So for anyone who has not been to Toronto, this is not what you would see the high-rises at in pictures. This is a very residential zone. And for anyone who has been here, it's on Dufferin Street, right next to Eglinton Avenue West. And the duration of our study was between December of 2020 to May of 2021. This is the community center on which the study was conducted. And what we're interested in is this roadway, and that would be our source. So our experimental site, we have three main instruments that were set up on the roof of this recreational center. First is the sonic anemometer, which measures the high frequency wind speeds. The second is an ultra high sensitivity aerosol spectrometer. This operates with a pump in which the pump takes in air and then the USAS subsamples from that pump in order to determine what the particle sizes are. And the aerosol that it collects, the aerosol sizes that it collects is 55 nanometers up to 1,000 nanometers. And the third instrument was a video camera, which just recorded the traffic on the road. So before we can even get to analyzing what the concentrations are according to the traffic, we first have to figure out whether the concentrations are coming from the vehicles or not. And the very first thing we do in that case is a tilt correction. So like I mentioned before, we're interested in the traffic that's on the road in front of it. In order for us to have that exact source area, we need to make sure that the wind direction is from the southwest, so it crosses over the road and goes up to our canopy. So because of that, the very first thing we do is a tilt correction, and this just rotates the anemometer to the axis to the average wind direction. And from there, we can actually calculate the theta, which is the most important step, because this tells us where the wind direction is coming from. So we want to make sure that it's between 180 degrees or up to 270, so we can neglect any other wind directions that are coming from around it. Once we correct the anemometer, we can move on to the eddy covariance flux. The eddy covariance flux is just a measure of the vertical turbulent flux, or the transmission of aerosols per unit time per unit area. For example, if we know what the number of aerosols at time 1 and eddy 1, and we know the number of aerosols at time 2 and eddy 2, we're able to determine what the vertical flux is at that point. However, the only thing that doesn't work out with this is the fact that fluxes can be produced anywhere upwind from the station. And what we're actually looking for is the turbulence or the flux that's produced on the road. That's why we have to go into a footprint analysis. With the footprint analysis, we have the advantage of isolating our flux that we're interested in just to the road. Also, with the analytical formula that's used for the footprint flux, we're able to also have conditions of stable and unstable atmosphere, since that's very important, because when in a stable atmosphere, you're not going to get as much mixing, whereas in an unstable atmosphere, you can have a lot more mixing. So this is just to conceptualize the idea of a footprint. What we would want is that the turbulent flux to be the highest on the road and ignore everything else. This is also a 2D footprint. So we have the X and Y direction of how that source area spreads. And in order to, what we're also doing is correlating with the amount of vehicles that are on the road. So we have the video analysis to do with that. So this is exactly what the video camera captures. It just captures the video of the vehicles going across the road. What we use is a average gray value to determine how many vehicles are on the road. So in this example, we have lane 1, 2, 3, 4. And if we have a car in lane 1, you're going to see that the grayscale value changes for all 4 lanes. However, this only takes into account the longest sequence. So the longest change in the grayscale will happen in lane 1. So it'll count that as 1 vehicle. We do have errors that arise with this. So in situations like this over here, where you have lane 3 and 4 and you have overlapping of vehicles, it will only count vehicle 3 because it'll have the longest change. Similarly, when you have large vehicles, such as a bus, which is very common in this area, we will have the software will only count the bus and nothing else around it. So there are 3 different techniques that are going to be applied in order to determine this. The first being a weekday versus weekend. So if we assume that the amount of vehicles during the weekday are greater than the ones on the weekend, we can look at the amount of aerosols or the footprint that's produced during the weekday than the weekend in order to compare how the sheer higher number of volume of cars affects the amount of aerosols in the atmosphere. Secondly, like I mentioned before, congested areas produce different driving patterns. So during rush hour, you're going to have a lot more acceleration and deceleration. Studies prior to this have determined that when you have more braking and accelerating, you're going to have more larger particles break down, such as non-exhaust ones. So when we compare rush hour traffic to regular traffic, it allows us to look at how changes in driving patterns are affecting the type and shape of the type of particles that are released. And finally, since the study was during periods of lockdown and post-lockdown where we had restrictions lifted, we're able to analyze daily and weekly patterns in a very reduced traffic amount setting to see how that improved air quality as well. So far this is the entire time series of the number of vehicles on a daily basis. This missing data over here is when the video recorder had to be taken home for processing. So that's what we're missing. Let's look at periods of where there was no lockdown versus where there was a lockdown. So this is the total traffic for the week of December 22nd to the December 30th, where there was no lockdown, compared to this one, which is April 29th to April 25th, 2021, where there was a lockdown. And we see that there is significantly higher amount of traffic during the weekday compared to the weekend. Friday was a holiday, so of course there's lower traffic. And when we compare that to the period of the lockdown, and this was a very harsh lockdown as well, so the only things that were open were supermarkets, we see that the traffic amounts during this week are completely normal and they're about the same. As well as we can see spikes in terms of the periods in which the traffic increases and decreases, and that's what's going to be used in order to do the rush hour analysis. I want to talk a little bit about concentrations within an urban canopy. So this is the average number of concentration with wind direction that's from 180 to 270 degrees from April 15 to April 26. So we're looking at a weekly and weekend difference. When we look at this plot right here, we should have around the same amount of particles if we did not do the flux and footprint. However, we see that the weekdays have much lower concentrations compared to the weekends. So this just goes to show that the importance of the flux and footprint analysis, because within an urban canopy, you can have particles that are released 2-3 kilometers down and they can register on the other end of the city. So this cannot quantify the amount of emissions that are coming from the vehicles. So in conclusion, preliminary studies have shown strong relationships between vehicular traffic and non-exhaust traffic. However, what we're trying to look for is how we can lower speed limits and allowing more free-flowing traffic, how that can actually impact how to lower particulate matter. And when we look at the grander scheme of things, as we move towards an electrification of all vehicles, we are going to see that non-exhaust emissions are the primary emissions in the atmosphere. Oh, these are just my references. Thank you.
All right, thanks. Yep, any questions? Last session of the day. Okay, well, if anyone has anything, feel free to jump in. Otherwise, we've since learned that there is a health break in the middle of the 6 talks in each session. So yeah, please take a break. Feel free to connect with Rhythm if you think of any questions later or any of the other speakers through the chat. If you want to start dialogue through the break, that's great. Otherwise, I'll start up again at 3:50 Saskatoon time, so in 13 minutes. So yeah, and as I said, please feel free to open discussion through the group as you please. Thanks.
Yeah, I have a quick question for the image processing for the counting the cars.
Yep.
How complicated it is? Like you said, it is video, right?
Yeah, so it's a software that's written that runs through all of the videos in order to see how the grayscale changes within every video.
What I mean is like you're kind of getting snapshots from those video frame, right?
Yeah.
And it's not that high resolution.
No, not as of right now. We actually are in discussion with another professor within the department who has a software which is actually able to look at the different, calculate the different vehicle speeds as well. So we're gonna see if we can process our data again, but this time looking at the different vehicle speeds, looking at the different speeds that the vehicles are going on as well.
Yes, I'm not really know the details in this kind of. I'm more meteorology guy, so
yeah.
But like I know some of those research has been done in my home country. So yeah, I'm just wondering like maybe diesel would be different from gasoline, for example, and it may be really hard for you to distinguish if like a diesel fueled small car versus gasoline fueled large SUVs are quite different. So
yeah, so what we're mainly focusing are on non-exhaust emissions, right? So these will be your brake wear and your tire wear.
Okay, so
so those are in every single type of car regardless.
So you're kind of getting rid of those. Okay.
Yeah, we're not
totally
on that. Yeah. Thank you.
Yeah, thanks.
Another.
Sorry, muted. There is also a question in the chat wondering if you've seen measurable differences between brakes on the different vehicle classes.
So as of right now, I have not, but there are papers out there that have noticed that difference. So there's a paper that I read where they found that bigger, older trucks with different types of brake pads have different sizes and the amount of brake wear that occurs. So if you have something, yeah.
I think you guys really need a good image processing. I've been working on image processing a lot, and it's quite kept secret by MIT because they're do a whole bunch of those military vehicles from just normal cars. And what if those are quite similar, like bus, like military cars are quite hard to distinguish from those. Like if they have like missile at the back, it's quite easy for them to distinguish. But if those are quite similar, maybe it's really hard. So if you can distinguish those old cars from new cars, maybe you need a good amount of images. Like maybe you can distinguish, like, I don't know, vans from 1960s from 2010 or so. So, and maybe how well maintained are also another source of making those tests or something. So yeah, it's interesting, but yeah, maybe that image processing algorithm should be really well maintained. And
It's very preliminary, it's true. There's a lot of companies that do that imaging processing for you for a decent cost. As Rhythm pointed out, it's being developed elsewhere too.
yeah,
One of
because
our
AI,
final talks in this session would be
yeah, AI is not really a magic words
Yeah.
for everything, because it's always making really foolish mistakes while humans are trying to determine or make a decision considering a whole bunch of other stuff in together. So yeah, but it's interesting. Thanks for
Mhm.
the response.
okay. I'm gonna actually take a quick health break, refill my water. So I'll restart. So if anyone else wants to continue speaking, by all means.
Are you Mohammed?
Yeah.
Oh,
Hello.
okay. Yeah, your audio seems good. Can you share your screen to make sure?
Is it good?
Seems good, but like, can you make it like a slideshow or like whatever presenter you or something?
Yeah, I mentioned.
Sometimes.
I don't know. I think there is a problem with full slide. Just show for me. I don't.
Yeah, if you have like
Yeah.
an
Is it?
additional monitor or something, maybe you can choose either one of two.
Yeah, I'm trying to fix it. If not, is it okay just to present like this?
Yeah, I don't think there's no problem unless like it's really hard to read, but like you can explain whatever in
Okay.
the slides, so I think it doesn't really matter. Just make sure every other presenters tested their audio with screen sharing. So I just want to make sure.
Okay. Okay. Thank you.
That'll be good. Yeah, maybe.
Sharing. Yeah.
Yeah, I will just. Yeah, I will just keep this one.
Okay, welcome back. Oh, if anyone went anywhere. But we'll continue now. So our next speaker is Joshi Shu, if we said that right, who will present on the impact of deep basin terrain on PM2.5 distribution and its seasonality over the Sichuan Basin in southwest China. So you're in, yep, presenter mode, and we can hear you.
Thank you.
So anytime.
Hello, everyone. I'm a Chinese visiting student and at York University from Nanjing University of Information Science and Technology. It's my pleasure to present my work here, and I'm reporting on impact of deep basin terrain on PM2.5 distribution and its seasonality over Sichuan Basin, southwest China. In recent years, major PM2.5 polluted regions distributing mega cities or city clusters, especially over China. Several susceptible regions in China have suffered from heavy PM2.5 pollutions, including the North China Plain, Yangtze River Delta, Pearl River Delta, and the Sichuan Basin. Compared with other flat areas, the Sichuan Basin is isolated by plateaus and mountains with a deep bone structure. So our study focuses on the distribution of PM2.5 in the Sichuan Basin. In the Sichuan Basin, there are intensive anthropogenic air pollutant emissions with a steep elevation drop to the west adjoining the Tibetan Plateau. Air quality in this region is strongly subject to Plateau's thermal and dynamic forcing. Weak air diffusion conditions favor the formation of PM 2.5 pollution involving air stagnation, shallow planetary boundary layer, weak near-surface wind field, and high humidity. And many studies concentrate on pollution episodes, but the lack of comprehensive assessment of the topographic effects on PM 2.5 seasonality. To explore the effects of complex terrain on regional atmospheric environmental changes, we target the Sichuan Basin to analyze the impacts of ventilation conditions, topographic forcing circulation, atmospheric thermal structure, and secondary aerosol process. First of all, I would like to introduce the main method of this work. Wolfram 3.8.1 model was employed with 3 nesting domains, and the detailed setting is also listed here. We designed 2 groups of simulation experiments. One is the terrain real experiment, which runs with the real terrain, and the other group runs with the altered terrain. In the sensitivity experiment, the basin is filled in all 3 domains, refers to the formula. 4 months of January, April, July, and October in 2017 respectively represent the 4 seasons. The difference between the 2 experimental results means topographic driving effects on PM 2.5 changes. After model evaluations, we firstly discuss the characterization of 3-dimensional PM 2.5 changes. High surface PM 2.5 distributes in the western and southern parts of the Sichuan Basin. It reflects the importance of plateau blocking in air pollutants accumulation, and the seasonal variations of PM 2.5 enhancement could be connected with the seasonal shift of East Asian monsoon from summer to winter. The Sichuan Basin is a major PM 2.5 source in southwest China. Prevailing northeasterly wind modulate near-surface PM 2.5 transport. We found the terrain forcing contributes from 40 to 90% to surface PM 2.5 levels in the surrounding clean areas. The phenomenon builds an important thought receptor relation driven by the basin structure. In terms of the vertical distribution of PM 2.5 changes, there are west to east horizontal gradients in 4 seasons, and the high concentrations of PM 2.5 stacked at the slope of the eastern Tibet Plateau with the terrace block. Especially in winter, a thick layer of the enhancement can reach up to around 4.5 kilometers. Such elevated PM 2.5 in the free atmosphere might alter the process of cloud condensation nuclei, radiative forcing, and precipitation in this region, and even transport to the downstream regions in the free troposphere under the mid-latitude westerlies. Air quality is strongly affected by meteorological conditions. In this part, we will analyze how basin terrain influence PM 2.5 concentrations based on our simulation results. In the planetary boundary layer, basin structure decreases ventilation conditions, for air pollutants accumulation. And the increased air temperature and the humidity are conducive to the secondary aerosol formation. These changes notably occur in the winter time, resulting in regional PM2.5 problems. And in the low troposphere, a vertical vortex circulation covers the Sichuan Basin under the influence of vessel ice, updrafts by the block topographic on Asian monsoon. The dynamic process seasonally oscillated from lower in winter around 2 kilometers to higher in summer between 4 and 5 kilometers. Even the atmospherical thermal structure is also changed over the region. Two warm layers exist in the near surface layer and the free troposphere. Such thermal structures could enhance the vertical mixing within the atmospheric boundary layer and inhibit the upward diffusion of PM2.5 into the free troposphere. In the end, sulfate and nitrate as the main secondary aerosols reflect the secondary formation of PM2.5. Here we calculate the sulfate oxidation ratio and nitrogen oxidation ratio for investigating chemical conversion rates. The SOR and NOR are significantly correlated with the air temperature and humidity. In this region, the increase of air temperature and humidity is found due to the effect of the basin terrain. As a result, aerosol heterogeneous reactions and chemical conversion for secondary PM2.5 are effectively accelerated in the Sichuan Basin region. The chemical conversion ratios are elevated with SOR up to 0.02 and NOR up to 0.22. And our main conclusion are as follows. Firstly, terrain effects are characterized by the elevated PM2.5 concentrations over the region. Secondly, deep basin aggravates PM2.5 accumulation within the basin and the transport to high altitude regions. Finally, regional thermal structure and the vertical circulation in the lower troposphere are revealed by terrain effects on interactions of vessel ice and the Asian monsoon for air pollutant diffusion and the formation of secondary aerosols. This concludes my report. Thanks for your attention. You can view it online or communicate via email if you are interested in the study. Thank you.
Thanks. That's very interesting. Any questions? I didn't fully catch, are the winds just generally always from the southwest, or did you exclude, or did you only look at when winds were from the upside of the basin?
I can show these pictures. There is only a channel at the northwest here, and the prevailing wind is always northeasterly in the basin.
Within the basin?
Yeah.
Okay. Well, outside the basin, is it typically from one side or the other, or?
Outside the basin is actually is the southwest westerly, yeah.
Which is the second steepest side, I guess.
Yeah.
Yeah. still time for more questions if anyone has. And then when you fill the basin like that, that actually has effects on the, you actually see the effect on the inversion layer. Like there is no inversion once you fill the basin.
Sorry?
So when you fill the basin and the second, the sensitivity test,
Yes.
does that eliminate the inversion layer in the model?
Yes.
Yeah, okay.
Okay, thank you.
That's really neat. Great, okay. Yeah, still more time if anyone, feel free to enter a question in the chat. I want to kind of keep it to the schedule, so I don't really want to start early. So yeah, if you think of a question, please feel free. In the meantime, Sepper, you could put your talk up, share your screen if you're ready.
Oh, so not me, I'm sorry.
Oh, yes.
Yeah.
Sorry. Yeah, there you go.
Yeah.
Hi.
I'll just give it a second, just in case anyone's coming in on schedule.
Right.
Um, that's probably close enough. So yeah, our next speaker is Sepper Fatih, who is, well, I guess this is from Environment Canada work with that group.
Yeah.
And this is a new plume rise algorithm, including the thermodynamic effects of combustion water in buoyant stack. So yeah, whenever you're ready.
Okay, thank you. So hello everyone. I'll be talking about this new plume rise algorithm that I've been working on along with my co-authors from Air Quality Research Division at Environment and Climate Change Canada and York University. So within this new plume rise parameterization, we are including the thermodynamic effects of the water vapor in the buoyant stack plumes. This new algorithm is currently being implemented and tested within the GEMAC model, which is Environment and Climate Change Canada's air quality model. And today I'll be sharing some of the theory behind the new algorithm, and I'll show you some results. So the GEMAC model is a fully coupled online regional air quality model with physical and chemical process representations. It has a subgrid parameterization algorithm for determining the plume rise from various sources, including tall industrial stacks from which high temperature and buoyant effluents are released, which rise sometimes to by a few hundred meters above the stack top. And the plume rise algorithm in the GEMAC model is based on empirical formulations by Briggs, and it calculates the buoyancy and momentum of the effluent at each model layer based on the ambient input information and the stack parameters such as stack flow rate and the temperature. Model predicted fields has been previously compared to observational data, including aircraft observations from two campaigns back in 2013 and 18 over the Canadian oil sands region. I'm showing an example in the right where SO2 concentrations are shown. Plotted are the model predicted concentrations as shown with that box, and also aircraft observations of the same plume and during the same time is also plotted as a function of time and the height. And as you can see, there's some overlap between the model predictions and the aircraft observations, but also there are some discrepancies, especially after 18 UT, which is the local noon, in terms of predicted plume height. So the negative bias that was observed in these comparisons for some species, so a number of species has been attributed to sometimes to the underpredicted plume rise for SO2 and NOx, and for some other species has been attributed to the missing aqueous phase chemistry, basically missing water and its impacts on this on plume behavior. So that motivated us to develop a revised plume rise algorithm where we include and incorporate the effects of water vapor in the plumes in our parameterizations. In the current phase of this study, we are focused on the impact on the plume rise, but in the future, we'll also be looking at the impact on the chemistry. So in order to be able to model the effects of water, we need input information, input data for water emissions. Unfortunately, water is not usually not directly measured by monitoring systems, and so we needed to derive an estimation for water emissions from emission rates for other species, either from inventory reports such as SEMS or from aircraft-based estimates. So for example, I'm showing here an example of aircraft top-down retrievals where aircraft would fly in what is called a flux box or box flight around the mission sources, and makes measurements at different vertical altitudes and then those measurements are translated into emission rates for the within box sources. So for example, if you have an estimate for emission rates of the CO2 using some assumptions like the fuel combustion equation you can see here, to estimate the amount of water that was also released from these sources. We also use aircraft observations to determine the plume heights and compare those to our model predictions for evaluations and also calibration. So the new plume rise algorithm is partially based on the previous algorithms, where we use empirical parameterization by bricks. In that formalization, the vertical and bent over plumes are treated separately using different coefficients for entrainment and the volume flux. So for example, for the vertical case, we have different coefficient alpha in this case and beta for the bent over case. That determines how fast the plume would expand and rise, and how much of the ambient air would be entrained into the plume. This algorithm, the buoyancy and the momentum of the parcel or the plume is calculated at each model layer and compared to the ambient conditions, the stability conditions, to determine whether the plume would be rising or it would stop. And from there, we can calculate the final rise. What we are adding to this parameterization is the effects of water. Water is released from stacks into the plume, as it rises, it expands, it cools down. If there's water in it, it can condensate, and latent heat would be released, which can increase the temperature of the plume and result in additional rise. The opposite can also happen, where you have, if you have excess liquid water, it can be evaporated, which takes energy away from the parcel and restricts the rise. So just show you an overview of the algorithm. We have at each model layer, we have the emitted water, the entrained water, whether it's in gas phase or liquid phase. We calculate the state parameters of the parcel at that height using the stack parameters and the ambient input fields, including the partial vapor pressure. We compare that to the saturation vapor pressure. If it's oversaturated, condensation can happen, which releases latent heat. The opposite can happen. If you have excess water, liquid water, evaporation can happen, which can take energy away. Both of these conditions can result in a change in temperature of the parcel. And as long as that is above a certain threshold, this is just a small value, we continue with recalculating the temperature of the parcel and the density of the parcel, and going back to calculating the other state parameters. So this cycle goes on until we converge on a solution at that particular layer, at which point we compare the updated value for the density of the partial to the ambient conditions. If it's still buoyant, it'll keep rising, and we continue or repeat the calculation for the next layer up. And as it goes up, it approaches the ambient air density, and at some point it will be equal or even heavier than the density of the air, ambient air, at which one we terminate this cycle and calculate the final rise, both for the vertical case and the bent over case. And following the recommendations from Briggs, we choose the lower of the two. Just to show you an example of the output fields from such calculations, here I'm showing vertical profiles for the same plume rise calculation. So up here I'm showing the condensed water as a function of height, and also temperature and density for the vertical case and also the bent over case. For instance, in this case, we have condensation happening at a few meters above the stack top. Releases latent heat that increases the temperature, results in a decrease in density and an additional rise for both cases. So for the vertical and the bent over, and that results, for example, for the bent over, in this case, 26% additional rise. And that is compared to previous predictions. And as I mentioned before, in our algorithm, we choose the lower of the two as our final answer for the estimated rise. I did these calculations for using model-generated fields and compared them to aircraft observations shown here with the dark dashed line as a function of time. And to that, I'm comparing the predictions from the older version, which are these gray bars, and the blue and orange bars are showing the predictions for the vertical and the bent over cases by including the effects of water. And as you can see, for the most part, for this case, all of them are performing kind of similarly, but you have these occasions where the older version, without accounting for water, under predicts the rise. But if you include that, you get better performance against the observations. So I did these comparisons for 10 different aircraft observations, 10 different flights for 3 facilities, and using these two methods, the old and the new algorithms, for 5 sets of input emissions and meteorology. And here's the summary of the statistics. I'm showing the normalized mean bias for both cases, and I'm showing the one that is performing better with a green color. And you can see for the most part, the new algorithm is performing better. And even for this single one, that you have the older one performing better in this case, then they're pretty close. So you have improved in performance. A quick glance into the performance of this algorithm in the GenMac model. At the top, I'm showing the old version, old algorithm, and in the middle, the new algorithm, and at the bottom, I'm subtracting the older one from the new algorithm. And for this time period, you can see the effects of condensation with the new algorithm, which predicts a higher rise. You can also see some diurnal trends in both of them, and you can see that for most of these, the new algorithm is predicting a higher rise. Having said that, there's some occasions where we see increased concentrations near the surface that we're investigating why these are happening. This can be due to several different reasons. One could be because plume is rising to higher altitudes for the upwind emissions, and that are carried over for longer ranges, and they're showing up at places that we didn't see with the previous predictions. And just to go back to the first slide I showed, you can see this diurnal effect happening at the local noon 18 UT. We can see it intensified with the new predictions. So just to give you the conclusions so far, including water vapor in the parameterization actually has an impact, significant impact on the predicted rise. We have seen plume rise, higher rise with condensation and without condensation. That is partially due to how we treat the layered calculations. And in terms of next steps, we'll be looking at sensitivity tests with the empirical rates that we're using, and we'll also hoping to look at the impacts on chemistry. And that concludes my presentations. I'll take questions if there are any. Thank you.
Thanks, Sepper. Very interesting.
So, Sepper, in all the times that I've seen you talk about this, it's never occurred to me to wonder about the difference between the bent over and the straight up plume. What's the justification of just choosing the smaller of them? I had always assumed it was about the horizontal wind speed.
Yeah, basically, like for a actual plume like the one I'm showing in the background here, you have some portion of it rising vertically and some portion horizontally, but the empirical formulation that is used commonly in a number of different models for subgrid parameterizations, they run these calculations separately for the vertical and bent over, and they choose the one that predicts the lower rise between the two. And the difference between them comes from the different coefficients that are used for interment rates, and using observations, past observations. Apparently this recommendation was developed to use the one that predicts the lower rise.
So,
And we can see it with our analysis too.
So it's basically an empirical relationship.
Yes. That's
okay.
correct.
Thank you. Thank you.
Yep. Thanks.
Okay. Sorry to interrupt. We should probably move on to the last speaker. So thanks, Sepper. I have questions as well, and I'll follow up with you just out of my own curiosity.
Sure.
So yeah, our next speaker is Mohammed Kushafar, who is from my own group at York University. And we'll also be talking about plumes, looking at automated plume rise measurements based on deep neural networks using video images. So, whenever you're ready, Mohammed.
Thank you, Mark. Do you have my voice? Mark?
Yeah, that's loud. Yeah, that's good.
Okay.
All good.
Thank you so much, everyone. Hello, this is Mohammed Kushafar. I'm a PhD student under supervision of Professor Gordon and Professor Sun, working on automated plume rise measurement based on deep neural networks using video images. Let's start with the definition. What is plume rise? Actually, when a smokestack releases pollutants, the resulting plume will rise due to momentum and buoyancy until it dissipates and is carried downwind at a constant height. This height is called plume rise height or plume rise. Plume rise influences how far pollutants are carried downwind, the concentration of pollutants at the surface, and where the pollutants will be deposited to the environment or inhaled by people, as well as the amount of greenhouse gases actually mixed into the upper troposphere. The parameterizations of plume rise prediction were developed in 1960s and 1970s and tested in 1970s and 1980s. Usually different models use a form of parameterization as known as the Briggs equations. Although the majority of air quality models use the equations, these equations that they're using, they have not been verified in more than 30 years since their original development and testing. Recently, in 2013, actually, an aerial measurement study was done in the oil sands development region at Alberta, Canada. It was demonstrated that the Briggs equations significantly underestimated the plume rise as these equations. These locations. Given the results of this study and the gap of more than 30 years since the equations were developed and previously tested, there is a need for further testing and maybe possible modification of Briggs equations based on modern observation techniques. At the first part, data collection and data preparation, we started to collect image data from Syncrude oil sands located in north of Fort McMurray, Alberta, Canada. 96 images were captured every day, and we have collected about 45,000 image data since November 2018. Also, we have collected about 1.6 terabyte of video data from Vale Copper Cliff Complex, a mining company in Sudbury, Ontario, since January 2019. We're working both on image data and video frames together. So we're looking for kind of real-time processing of the plume rise. Sorry. So we were looking for a just system and let's say model just to recognize the plume rise in every image on every frame, video frames. MASCAR CNN is a member of region-based CNN family. It represented the highest accuracy regard COCO dataset segmentation challenge, and afterwards, it's used widely in different segmentation tasks. MASCAR CNN is an instance segmentation deep learning model, and as let's say is an extension of FastRAR CNN, which can create pixel level masks for the object that here is plume cloud, beside object localization, the bounding box, and the classification task, which is telling us that this is the object or not. As you can see in the picture, let's say the most important part of this model is the region proposal networks. Region proposal network is a deep, fully convoluted network which proposes regions and serves as the attention of the MASCAR CNN. Here, attention is the smokestack that we're looking at. It means that RPN helps us to selectively focus on valuable parts within the input images. This network takes an image and gives a set of region proposals besides their objectness scores. We have done two different modifications. The first one was RPN structure modification. Let's say based on our collected data, there is a common area within the images in which the plume cloud appears in 97% of the time. It is right, level, or straight. Thus, the region is, in the area where we should try to find the plume, it is the, red box that you've seen in the picture. Therefore, the sliding window should span and propose the anchor boxes which are inside this box, not out of that. So this really have increased the accuracy of the system. The second case that we worked on, let me tell you, for example, we have two smoke plumes here. The bigger box, green box, and the smaller one, and all the anchor boxes around. So we wanted to minimize the distance of these boxes to the smokestack end, which we have called in our paper hot point. Hot point is the end of the smoke. We know all of the let's say, object and plume cloud is coming and exits from this point. So it's very important just to minimize the bounding box. This thing, again, have just significantly increased the accuracy in our system. We've started a train job following with validation of testing phases using 1K various training images and 200 validation images to fine-tune a pre-trained mass Gaussian network to deal with bigger set of plume cloud types. As you can see here, with different backbone of, ResNet 50 and ResNet 101, this is the pure mass Gaussian that we've applied for the data set that we had, and you can see the metrics. And this is the proposed model. Proposed model that the structural modifications have applied to it. So with the ResNet backbone of ResNet 50, you can see mostly the metrics are getting better, and we will see new visual metrics too. I haven't tried to ResNet 101 because as you can see, because of overfitting, we couldn't use mass Gaussian with the backbone of, and you can see the metrics that are not that much good. So we didn't try ResNet 101 as a backbone of our model. So we get with the ResNet 50. Here is some visual experiment results. The left is the output of the model when we're using actually only the pure mass Gaussian, and the right images are the output of the model, just the proposed model. The percentage that you've seen here is the objectness score that models gives to the plume. Again, we need to just increase the accuracy. We know about it, but these steps that we've just taken to deal with the plume, with the translucent edges are kind of significant. And yeah, that was the updated results that the latest result we've got from our model. Thank you for the Buffalo Environment Association for the camera stations and collecting the data, and the project is funded by Lausanne School of Engineering at York University. These are my references, and thank you so much for your time.
All right, great. Thanks, Mohammed.
Thank you, Mark.
Any questions?
I'm curious if you hunted for any false positives. Did you ever detect plumes in scenes where there were no plumes?
Exactly. Yeah. Actually, good question. Let me just go. Yeah. When we're looking at the last or MSE, we have some kind of results that we've got false negatives for that. So that's why we had kind of discretion in these. But yeah, again, we have here the false negatives too.
But what about, false positives? Like, did your algorithm ever say
Exactly.
There was something going on when there wasn't?
Exactly. Actually, when we're talking about the precision, we have talked about these false positives, yes, you said, right?
Yeah. But like, what would cause those? Like, what kind of scenes would look like a plume but weren't? I'm just really curious.
Okay, yeah, exactly. As an experience that we've got, we have get through different data when the atmospheric is kind of unstable and we are in a cloudy atmospheric, atmospheric condition, it happens.
Interesting. Okay, thank you.
Cloudy images most of the time, if you want to just specify that.
Mm-hmm.
Yeah, they look a lot like clouds, it's true. Any other questions?
Just have a quick follow-up question. Like, I'm not really professional in here, but like, just in case if you're dealing with whatever image processing and whatever like a lookalike, whatever you want to detect is happening, is there any way you can discriminate or like you can distinguish from that kind of thing? Let's say if you have like a dusty plume, for example, and you don't really like it, but what if the algorithm says yes? Is there any way to say, let that algorithm to say, hey, this is not you want to detect, and like say no about that kind of thing? I'm just wondering.
Yeah, exactly. Yeah, no, again, good question. So totally, when we just prepare the data for our neural network, we should just cross it out. I mean, the data that we're using to train the model, it shouldn't have any dust. It should be kind of just let's say the pure plume cloud. But totally, I mean, according to what we've got from the science, I mean, different methodologies have different kind of defect, I mean, deficiencies. So yeah, when you're looking, I mean, as a human, when you're looking at a plume, sometimes you cannot recognize this is a plume or cloud or what. So actually, when we have problem, if it is dust, if we have another smoke sources that is coming to the, we have kind of deficiencies in vision-based methods that we have,
Yep, because like one of the drawbacks of having neural network as like your main engine would be because there's like always like black box. You cannot really see inside what are those, and sometimes we cannot even fix it if there's something wrong. So maybe it may be sensitive, whatever you provided to algorithm to train at the very beginning.
Exactly. Yeah.
So,
if you look at totally of it, it shouldn't be just used alone. If it will be, I mean, modification of other, I mean, physical simulations, that would be very great. But alone, visually, you cannot see all the time the plume and recognize, here is the plume. Not only.
There's just a quick reference. If you want to make it easier to whatever fixing neural network, I think there's some way to combine neural network with others, like fuzzy logic, for example. So there's some ways to fix it, but like, I'm just curious. Thanks for the answer. Yeah, thanks.
All right, great questions. So I guess we'll wrap up and thank all of the session speakers for some really interesting, well-presented talks. And thanks for hanging in till the end, especially those in the east side of the country where it's a little later. There is, I guess, an icebreaker in 25 minutes or so if you want to stick around for that chat. But and again, a reminder, there's a fourth air quality session on Friday morning at 8:25 Saskatoon time. So I hope to see everyone there. And again, thanks for the speakers and everyone for attending. So take care.
Yep, thank you very much. I will just stop recording here. Yep. Thanks for staying this late.
Yeah.
For the first day. Yeah, thank you very much.
Go have dinner now, but thank you for your help, and that's been great.
Bye-bye.
Thank you.
Thanks.
Thanks.